Hi, my name is Rohit Kumar Singh, and I'm the teaching assistant for the course Wave Optics. And this is the 10th live session. And today we will discuss polarization of waves and concept of Jones matrix. And so let's start. So I already discussed little bit of polarization, I think, in the first lecture or second lecture. So but today we will deal with it quantitatively. So yeah, diffraction is over now. I mean, we covered almost all the topics, relevant topics. One topic that I missed was Fabry-Perot interferometer, but that was from interference, and we will I will try to cover that in an extra session, like I told you earlier. So okay, so today we are discussing polarization. So okay, so polarization of waves. Now this polarization is very common phenomena. Okay, so if you take a string in your hand and you oscillate it, it will do like this, right? So this is basically a polarized wave, as long as you are oscillating it in a single plane, right? So if you are oscillating it will be confined to a single plane if you are oscillating it just in one direction, and this is called basically polarization. Okay, so you have confined the wave to a single plane. Okay, that is it. So let's first talk about these waves on a strings, because this is most simplest wave that you can think of. Okay, so waves on strings, and these kind of linear, so these are called linearly polarized waves or plane polarized waves, because they are confined to a single plane. Okay, so in terms of 3 dimension, so you can confine these waves in, suppose, xz direction. So I'm drawing, let's draw some coordinates. So suppose this is the x axis, this is the y axis, and this is the z axis. So you are oscillating the wave from in x direction only, so you will have plane polarized wave in xz plane. Okay, so basically if you represent it with a vector, it will look like this. So this arrow represent the oscillation, like at each point of the string is oscillating in this only the x direction. Okay, there is no oscillation in y direction, and mathematically you can express it with the wave equation. So x will be given by the amplitude a and the cos or sine. So we can choose any one. So we can choose cos kz minus omega t plus some angle phi, which is the phase difference. And in the y direction, since there is no movement, no oscillation, it's 0. Okay, so this represent a linearly polarized wave in xz plane. Okay, sorry, not xz direction. And similarly you can have linearly polarized wave in xz plane. So z is the direction of propagation of the wave. Okay, and for yz plane, in x direction there is no oscillation, and in the y direction you will have the wave propagation given by this equation. So we can draw this. This is x, this is y direction, this is z direction. So now the wave is confined to the yz plane, so it will look like this. Okay, so it is oscillating in y direction. Like this. Okay, I'm bad at drawing. Anyway, you got the idea, right? Now that's no, these are two very common direction of polarization, but in general you can have any plane of polarization. So like you can rotate it, right? You can have any general angle. You don't need to confine it to xz plane or yz plane. This is just for illustration what is a plane polarized wave. Okay, now you can have some interesting polarization like circular polarization. These things you can make it in your home. Just take a string and try to polarize it. So circular polarization, you can rotate your hand in a circular motion holding a string, so it will produce a wave like this, right? This is also a wave where the points on the string are moving in a circular direction, right? Now how to represent it in terms of wave equation? Now you see here both x and y, you have movement both in x and y direction, right? So both will be non-zero, like you have something in x direction and something in y direction also. Okay, so let me write the wave equation and then I'll tell you how these represent this circularly polarized wave. Okay, so x direction, in x we have a cos kz minus omega t plus phi, and in y direction we have minus a sine kz minus omega t plus phi. So you see the y, in the y direction the wave is out of phase by how much angle from the x direction? Here it is cos, here it is sine. So what is the phase difference?
Pi by 2.
Yeah. So if you write a wave equation which is pi by 2, which is pi by 2 phase difference, okay, between x and y direction, then it will represent a circularly polarized wave. And also the amplitude has this negative sign. So to see this, what you can do is you can square both of them, RHS and LHS, and add them, and you will get this, right? And what is this? This is a equation of a circle, remember? So that's why, I mean, so basically when you have a variation of x and y like this, then the x and y will trace a circle, okay? And that's what, so each point on this string are part of a equation of a circle, okay? So that's why we can say that it is a circularly polarized wave. So this is how you can mathematically represent it. And this will and so minus and plus sign will basically make it either you can rotate it clockwise or counterclockwise. So that will be determined by this negative or positive sign of the y component. Now this is fine. So now you take a string and start oscillating it in a single direction, and you produce a linearly polarized wave like this. Okay.
Sir, why there is a negative
Sorry.
amplitude with this y equation? Why there is a negative
Oh,
a sign?
because we want to have a clockwise. So basically when x is positive, okay. So let's look at here. Okay, so this is your y direction, this is your x direction. Z direction is basically coming out of the screen. Okay, so when your x is positive, that means you are in the upper half, and if your y is negative, so like you have a point here, right? Then in the next time you will have x more positive, or you will have next point here and so on. So it will be, so you will see a counterclockwise rotation, and if it is a plus sign here, then you will get a clockwise direction. So it is just the direction of rotation. Okay, plus minus determines.
Okay.
So you can fix the z. We will do this calculation. Okay, you can fix z equal to 0, and then you can check for different time. Okay, we will do these things later. Okay, so yeah. Now coming back to the linearly polarized wave. So you have a linearly polarized wave like this, and you put a narrow slit like this. Okay, so the wave is coming here. What will happen? It will simply pass through, right? I mean, I'm considering now the slit width greater than the lambda. Okay, so there will be no diffraction. So it will pass through like this. But again, if you keep a narrow slit in the transverse direction, now what will happen? It will block it, right? And you get nothing here. Is it okay? Like this angle is just perpendicular to the angle of the oscillation of the wave. Okay, then there will be no transmission of the wave. Now this is very important. This so for a wave on a string, you can use. I mean, this is very simple, but because you can see whether the wave is linear in transverse direction or in longitudinal direction. But for a wave of light, for electromagnetic wave, we don't know whether it's oscillating in a transverse direction or in a longitudinal direction. So this kind of so if you can create a device which serves this purpose, then you can actually determine the the direction of oscillation of the waves. Okay, so what I'm saying is so the white light is unpolarized. Okay, so what do we mean by unpolarized is it is vibrating in all directions. So we represent it like this, okay? So it has not it doesn't have a a spatial direction of vibration, the white light that we have everywhere. So it is an unpolarized wave. But if you put a polarizer, so this we called polarizer, okay? So normally, so have you ever seen, have you ever put on goggles, like dark glasses? So what goggles are basically? They are basically polarizers, okay? I mean, they contain polarizing material. So that's why the intensity of light reduces. Polaroids, or there are many devices. So basically they are made up of some materials. They are mostly made up of quartz or something else, okay? So what this, and they have a optical axis. So basically they act as a narrow slit, okay, like this, like for the waves on a string. So okay, effectively what they will do is, in the direction of optical axis, they will polarize the waves of the light, okay? So you will get only a polarized wave after the polarizer in one direction, okay? And then what you can do is, you can put another such device here, okay, and start rotating it. So if you put it like this, it will let the wave pass through like this. But when you start rotating it, it will the intensity of light will again reduce, right? So what I'm saying is, suppose you have one polarizer here, okay, and you have another polarizer on top of it, and you have light coming from the bottom, okay? And so if you keep it like this, you can see the bright light. But when you start rotating it little bit, the light will become dim, and when you keep it like this, there will be no light. Why this is happening? Because you have already polarized it, and then when you are rotating it, you are again trying to polarize it, but it is already polarized in one direction. So what will happen is, it doesn't have any component in other directions, okay? And these polarizers, they only let the light pass through in one direction, okay? So you won't get anything when you rotate it in a perpendicular direction. So this second polarizer, it's actually called analyzer. So it analyzes in which direction the light is polarized by the polarizer, okay? So it depends on the angle between this and this. So there is an angle, right, theta. Anyway, so this we will teach, this we will also study later. It's called Miller's law. It has a formula also, but we don't need here. Just I wanted to introduce this concept of polarization. So yeah, we can use polarizer to polarize unpolarized light. That's it, okay? We will see later how does this happen, like how these quartz do this polarization, and later on, like there is something called birefringence and various other things. We will study it later. Okay, so just remember it. Yeah, we can have unpolarized light. Okay, now you can ask, how can we make an unpolarized wave with our normal string, like waves on a string? So you can make it by randomly, like in a very short time. If you can randomly oscillate the string, then you will have a unpolarized wave on the string also. But the light waves that we have everywhere, they are unpolarized basically. Okay, so this is fine. Did you get some idea about polarization? You have any question? I'll move to another topic otherwise. It's simple, no? Yeah. Okay, so now let's see what happens when we superpose two polarized waves. Okay, so superposition of two basically polarized, plane polarized two plane polarized electromagnetic waves or light waves. Okay, let's see what. So now we move from the waves on a string to light waves or electromagnetic waves. Okay, and we have already seen there, like we saw here that the superposition of two waves on a strings, two plane polarized waves on a string gave you a circularly polarized wave, right? So these two individually are just plane polarized waves, but when we superpose them, they gave us circularly polarized wave. So something like this also happens for electromagnetic waves. So we will quantify that. Okay. So let's see, we have two electromagnetic wave given by the vectors E1. So it is in x direction with amplitude A1 and propagating in z direction. So this is linearly polarized. I am writing LP for linearly polarized. And we have E2, which is also in x direction, and this is, so it has phase theta 2, which is different from theta 1. So we are keeping it general. Okay, this is also linearly polarized, and so two linearly polarized wave, if we superpose them, electromagnetic wave, we will get the resultant vector will be also in the x direction, right? And given by this equation, and this theta is the resultant, the phase of the resultant vector. And we have done these calculations, right? You know that the resultant amplitude is given by A1 square plus A2 square plus 2A1 A2 cos theta 1 minus theta 2, and similarly the resultant theta also you can calculate tan inverse of the combination of A1 and A2. So these formulas you already studied in like first or second lecture. Okay, now the interesting thing is what happened when instead of so because here we saw, if you have the superposition of waves in different direction, then you get something interesting like circularly polarized. So what happened if we have our second wave in a different direction, like in a y direction. Okay, so here when we had both of the waves in same direction, you get again the linearly polarized wave, okay, in x direction or in xz plane. But what if your second wave is in a different direction, like in a y direction, polarized in a yz plane, and let's write it amplitude as b. And it has a phase difference of theta. So here even let's write it like this. It is in x direction with amplitude a, and I am putting the phase angle 0, so that the phase difference between them will be just theta. Okay, it's fine. So now for this kind of waves, what will happen is, so you can see, so there can be two conditions. So it all depends on the theta. Okay, so if theta is multiple of pi, where m is where m is equal to 0 plus minus 1 plus minus 2 or some, or like this, then the resultant wave that you will get is also linearly polarized. Okay, so like we had here, like we had here, but this linearly polarized wave will be at an angle to this x and y axis. Okay, it will be not in either in x axis or y axis. Here in this case, the resultant wave is polarized in the same direction as the the components, but here the polarization will be at an angle, like the resultant wave will be at an angle to x and y direction. So to we can calculate that angle, and we can see, like you can intuitively see how this happens. So so now let's assume that let's assume that we are looking at the wave at origin, like at z equal to 0, right? So this we can assume, because we are not interested in the propagation of the wave. Okay, in z direction nothing much is happening. Whatever is happening is in the transverse direction. So we are fixing at one point in the space, and we are looking at the variation in x and y direction. So that's why we put z equal to 0, so that the Ex is now basically cos omega t, and the y component is now, so if you put m pi here, you can write it like this: minus 1 to the power m b cos omega t. Okay, because see, if theta equal to 0, then you get b cos omega t. If it is plus pi, you get plus 1. Yeah, if it is even, or if it is even, you get cos. If it is odd, you get minus outside, right? So that's why minus 1 to the power m you can keep here. So if m is m is even, you get plus, m is odd, you get minus sign in front of it. Okay, and then if you divide these two, what you get, Ex by Ey is plus minus of a by b. So either plus or minus depending on the value of the m. And what is this? This is a equation of a line, right? Straight line, basically in which plane? XY plane, right? So you see that you see that the vector, the vector of your resultant waves are basically part of a straight line, and so they are linearly polarized. And this is also independent of time, so independent of t. So it doesn't matter at what time you are looking at. Okay, always it will be straight line in the xy plane. So you can visualize it like this. And also this resultant E will be at an angle phi, okay, and this phi will be given by tan inverse plus minus A by B, okay. Now let's try to draw it. So you have let me, so this is the x direction, this is the x direction, and this is the y direction, okay. So for these two waves, if so let's first draw if b is 0, so you don't have the y component, so this is the ex, so it is oscillating in x direction, fine. And similarly this is for a equal to 0, you only have the y component, so this is your Ey, right? And now their superimposition will leads to, so this is the x direction, this is the x direction, this is the y direction, and their superimposed wave given by E will be a straight line, okay, making an angle phi from the y axis, okay, and this will be A and this will be your B, right? So this is when theta equal to 0 and let's say B is equal to 2A or something. Now you can also draw it for theta equal to pi. So for theta equal to pi, it will let me draw another diagram. Okay. So for theta equal to pi, you will have the resultant like this. This is x direction, this is y direction, this is the angle phi, okay. So this will be your A and this will be your B. Here B will be like 0.5 of A something. So this is just one visualization. So what does this mean is whenever you have two waves which are linearly polarized in x and y direction respectively, the superimposed wave will be also linearly polarized at an angle phi given by this angle, okay. So it depends on the ratio of A by B, whatever the angle will be, okay. Is it fine? And the theta should be like integer multiple of pi, okay. So this is for theta equal to pi.
Sir, what angle you are talking about?
This phi angle. Wait, there are two angles, so don't get confused. One is the theta. What is theta? Theta is the phase difference of uh, the y component from the x component. Okay, that phase difference should be integer multiple of pi. Then you will have linearly polarized wave. That means the wave will be a plane polarized. Linearly polarized means plane polarized. That will be confined in a single plane. Okay, then that plane will have an angle phi with respect to this y or x direction, depending on the ratio of A and B.
Yeah. Okay.
Okay,
I understand now.
and this minus and plus sign, this depend on the the theta, right? If it is 0, you will have plus sign. It is 1, you will have minus sign. Then if you have 2 again, 2, it will again plus sign, then 3 minus sign, and so on. Okay, so it depends on the plus minus sign, depends on the theta, and this phi angle depends on the ratio of A by B. Understand? Okay. Now, yeah, this is fine. So what what will happen if you have other than so what will happen if now you have theta not equal to integer multiple of pi, right? So for example, you will have ex, like let's take theta equal to pi by 2 first. Okay, and for now let's put b equal to a. So the amplitude of both are same. Okay, for now. So now your two components are in x and y direction can be given like this. Ey will be what? Sin omega t, right? Because it has pi by 2 difference. Now to see, so this now you remember, this is the same as this, right? And for this case we had what we had circularly polarized wave, right? So that should also follow here. Okay, now to check that, what you can do is, let's draw again the axis. So this is y, this is x. Okay, and yeah, and let's calculate these values at different time frames. Okay, so let's check at t equal to 0. So at t equal to 0, you have ex is equal to a, right? And you have ey equal to 0, right? So at t equal to 0, you get a point here, here in the x direction. Right? Now let's go to another time. So let's at t equal to, let's see at t equal to pi by 2 omega. So pi by 2 omega is what? It is basically time period by 4. Omega is equal to 2 pi by t, right? So that's why we are taking this time period, this time, 1/4 of the time period. Okay, so at t equal to pi by omega, you can see the ex will be what? minus a, right? Cos pi, no, sorry, it will be wait,
Yes, minus 8.
it will be minus a.
No, it's pi by 2 omega.
It's pi by 2, right? So cos pi by 2 is, oh sorry, it's 0, right? Yeah. And ey will be sin pi by 2, which is a. Fine. So now you go here. Okay, so from here you went here. Okay, and similarly for next time frame, which is pi by omega, you can see that ex is equal to, so at pi by omega you have again you have cos pi, which is minus a, right? And ey will be 0, so you go here, right? And then at the next time, which is basically 3 pi by omega, sorry, 3 pi by omega, you will have ex again 0 and ey will be minus a. So you go here, and then again from here you will see that at pi 2 pi you will go back here. So you are rotating in a circle of radius a, right? So for theta equal to 2 you get circularly polarized wave. Okay, like we thought, like we saw in the case of waves on a string. Fine. And similarly you can check at other angles, like what happened at pi by 3, theta equal to pi by 3. So this I'll leave as an exercise, so you'll see that. And also now you see the direction of rotation, it is clockwise direction, right? So this is called circularly polarized, like what it has an acronym like
Right circular.
right circular, yeah, RCP. So it is right circularly polarized. Okay, and similarly if you have this angle, like instead of pi by 2, if you have theta equal to how will you get left circularly polarized? I think 3 by 2, yeah, 3 at theta equal to 3 pi by 2 you will get left circularly polarized, and so on. Okay, and for pi for theta equal to pi by 3 you will see that you will get an ellipse. So right elliptically polarized. Okay, so now you see this is very interesting. Let me show you how it is interesting. Yeah, so what I said, at theta equal to pi by 3, if you calculate the same thing in the same way, you will see that you get a elliptically polarized wave. This is elliptically polarized wave. Okay, in this direction. So now what you saw, for theta equal to pi by 2 you got a circle. Okay, and for theta equal to pi by 3 you get an ellipse. Okay. Now what do you expect at theta equal to let's say pi by 6? Can you draw an analogy? So let me show you. So at theta equal to 0, what do you get? You get a linearly polarized wave, right? So what happens in the middle of these angles? Can you see some pattern? So nature always has pattern. Sorry?
Transitions from a straight line to circle.
Yeah. So this straight line, if you increase your theta from 0 to a very small angle, you will see that this straight line will go, it become like this, okay? And then it will start getting broaden, then you get an ellipse, then again you will get a broad, like a big ellipse, and then at theta equal to at theta equal to pi by 2, you will get a circle. And then after the circle, after pi by 2, the direction will reverse, okay? And you again go back to this straight line, this kind of a straight line. So you will get an ellipse like this at 3 pi by 2, and then again at theta equal to pi, you will go to a straight line. So you see there is a nice pattern. From this direction you will have it will break the degeneracy, you will start getting broad, and this straight line become a ellipse, and then this ellipse will become bigger, and then it will become circle at pi by 2, and then at a angle and then it will reverse the direction, again it will go ellipse, and then you will get again a straight line at theta equal to pi. Okay, so from this thing, so as theta increases from 0, you go to this, then it becomes circle, then you go to this, then you go to this, and then you get a straight line at theta equal to pi, and this pattern repeats, okay, after again I mean in each pi. Beautiful, right? So yeah, just keep this in mind. Okay, so do you have any question here? Okay, if not, then let's move to another topic called Jones matrix. So this is a matrix formulation of studying polarization, and it's very helpful. So I'll show you how. So there are some. Have you guys studied the quantum mechanics ever?
No, sir.
Oh, you have not studied quantum mechanics. Okay, no problem. You know vectors, right? Yeah. So okay, and you know matrices, and how to multiply matrices, matrix multiplication. Do you know? Okay. So then it's fine. So okay, Jones matrix. So okay, so let me write again the polarized wave. So suppose now we are looking at x linearly polarized wave in x direction, which is given by, so let's call now the amplitude E0, it doesn't matter. So earlier I was writing it cos kz minus omega t, right? Let's put the phase angle 0. So instead, and in y direction there is nothing, so it will be basically 0. Okay, so for our convenience, instead of this cos, what we write is we write it in terms of exponents. Okay, so like this, and the real part of this wave is basically the is basically the electric field. Okay, so it is understood that the real part of this exponential is basically our electric field, but we are representing it like this. Okay, so what this representation allow us is basically simplification of calculation. That's it, nothing else, because it's very easy to multiply 2 exponential rather than 2 cos or sine thetas, right? So that's why. Anyway, so this kind of also this kind of exponential representation can be written in terms of matrices. Okay, or let's call it vector for now. So we represent the vectors like this. This is called ket. Okay, so let me first write. I will tell you what does it mean. Okay, so here this is this x ket of x is basically 1 0. This is called ket x. So this 1 0 is a 2 cross 1 matrix. Okay, so this is like a, so in vector algebra there are unit vectors, right? I, j and so on. So what is I? I is the unit vector in x direction, right? And j is the unit vector in z in y direction, right? So similarly, this is a unit vector. Okay, it has a so if you calculate the value of this vector, it is 1. Okay, so how do you calculate the what do you call magnitude of this vector? So you basically multiply it with its self conjugate. So the conjugate is basically this and this and this, you get 1. So it is a unit vector of in x direction, which represent this this polarized wave in x direction. Sorry, it is, you have to take determinant. I know it's a little confusing, but okay, just bear with me. And similarly, y the linearly polarized wave in y direction, it is it is given by, so Ex in x direction you have 0, and in y direction you have E naught e to the power I kz minus omega t, right? And this can be written as this can be represented like this, sorry, y, where this unit this y ket y is given by this matrix. So 0 1, this is ket of y. Okay, so this is like a unit vector in y direction. So what we have done basically is uh, so instead of this expression, this complex expression, we have now reduced our electric field to a vector notation or a matrix notation. Okay, so vectors and matrix are very related things. Like uh, you can represent all the vectors with one like 2 cross 1 matrix. Okay, so that's what it is here. So this is kind of a vector. It is represented by a 2 cross 1 matrix. Okay, now this is so you have now the y polarized linearly polarized wave in y direction, and then you have linearly polarized wave in x direction. Now we can represent similarly a circularly polarized wave. Now how to do that? So for suppose right circularly polarized wave, what do we have? The expression from earlier. So we have this kz minus omega t, and in y direction it should be shifted by pi by 2, right? So in y direction you have kz minus omega t plus pi by 2, right? Which so you know that e to the power I pi by 2 is just I, right? So you can take I here, iota, and you are left with this. Because e to the power I pi by 2 is nothing but I. Can you derive this expression? It's easy, right? You know that Ex can be written as cos x plus I sin x. Sorry, e to the power ix. Yeah. So using this you can see it is just I. Okay. Now, so we have this and this components. So now it's easy to see. What is this? This is just E naught x, right? This is a linearly polarized wave, and this one is I of E naught y, right? And if you add them together, what do you get? So I'm adding this plus this. So this is E naught 1 0 plus I E naught 0 1, right? So this will be E naught 1, sorry, E naught 1 by I. Right? So 1 plus 0 and then 0 plus I 1. You know the matrix addition, right? So A by B plus C by D is equal to A plus C, B plus D. Okay, so that's what I have used here just. Is it fine? So this is your right circularly polarized wave. And since all the vectors should be normalized, okay, so you can normalize this vector. So let me write. So normalized vectors are given by this expression. Okay, so why do we normalize a vector? So basically normalizing a vector, we make the length of the vector equal to 1. Okay, so just for our convenience we can normalize this vector also, and after normalization, so it will be just under square root 2, right? 1 by I, because A is 1, B is I, so A square will be 1 and B square is also 1, so you get under root 2. Okay. And similarly, if you do this thing for left circularly polarized wave, you will get this expression. Okay, there will be minus sign. And so yeah, and we saw here that the circularly polarized waves are the superposition of two linearly polarized waves. So that you can also write it from here. So you can see that this is nothing but equal to square root of 1 by 2 into x plus I y, kit x plus kit y, right? And this is nothing but x minus y. And similarly, you can invert this equation to write x and y in terms of right and left circularly polarized wave, right? So you can add these two equations and you will get x is equal to, which is 1 by 0, 1 0 matrix. This will be equal to RCP plus LCP, right? And the y will be, if you subtract this to this equation, you will get square root of 2i RCP minus LCP. So now you see, it is very it is very simple algebra to add and subtract these waves. So this would not have been possible if we were working with this wave equation, right? Now it is very simple to add and subtract and see which is the superposition of which and all these things. So that's why this Jones matrix formulation is very convenient for calculation. Now tell me, if you have understood it, then tell me a simple. I'll ask you a simple question. So how will you represent a wave, okay, which is polarized at an angle alpha? So alpha polarized. Linear. So I'm talking about linearly polarized. Okay. So I'm talking about, so this is x direction, this or this is x direction, this is y direction. I'm talking about how will you represent a wave which is at an angle alpha to x and y in this notation. So suppose this is a vector. This is a wave. Let's represent it by a. It's a vector. Okay. How will you represent it? Any idea?
We take k x and k y as a unit vector.
Wait. Sorry, yeah.
I think k x and k y will be written as a unit vector.
Yeah. Great. Okay. This is unit vector. Then what will be the magnitude? So think about it. So this is a vector, right? How you represent vectors? Some some magnitude, then I cap plus some magnitude j cap. So instead of I and j, you have the ket y, x and ket y. Now what will be here? What will be the magnitude, amplitude, components? Yeah, what will be the components? And this A is a normalized wave, okay? So it has a unit 1. So what will be the components?
Cos alpha and sin alpha.
Yeah, cos alpha and sin alpha. Great. And this will look like just in matrix terms. This is only this, right? So this is a alpha polarized wave. Oops, I ran out of space. I wanted to discuss one more thing, little small stuff. No problem. Okay, yeah, this is then fine. Can I remove this part? I want to discuss one thing. Sorry. Oops. How do you increase the? Oh yeah. Okay. Yes. Okay. So now you have a polarizer, okay, or we call it polarizer, or any material you have. So we call it phase retarder. So it is like it is a kind of polarizer, okay, and it has a thickness d. So what does it do is basically it delay the phase of the waves. If any light wave passes through it, it basically changes the phase of this wave. Okay, how it changes the phase? So basically this phase retarder is made up of some material. It's basically quartz or calcite material, and it has some refractive index, right? So and it has different refractive index in different direction. Okay, so in x direction it has a refractive index nx, y direction it has a refractive index ny. Okay, so you know that the wave passing through a material will have you know, uh, will go like the velocity changes, right? So the frequency remains the same, but the velocity and wavelength they changes. So how the velocity changes? It basically changes by this, right? So this leads to, you know, change of the this basically the wave vector, which is given by 2 pi by lambda, right? Because lambda changes by this value, right? So the wave vector changes like this. So earlier, when you had the electric field, sorry. So in vacuum, your electric field was e to the power I kz minus omega t, right? So now omega will not change, so this factor will not change, but this factor will change, right? So now inside the inside the material, this part k will become suppose your because it depends on the this refractive index. So this k will change to a k prime, okay, and that will lead to a phase change, okay. So basically we can write it so this is now k prime, but it depends on the thickness of the material, okay. So let's call it x. So we are writing the x component of the light, d, and then whatever you had in the vacuum, okay. So this kx is basically 2 pi by lambda nx, okay. And similarly your y component at z equal to 2, so this x component is at z equal to d, ex at z equal to d, okay. And then similarly your y component at x equal to d at z equal to d will have this value, where ky is basically 2 pi by lambda ny, okay. So now they have a phase difference, ex and ey, and the phase difference is given by kx minus ky d, right? Which is just 2 pi by lambda nx minus ny d, okay. And so you can write this these two equation in terms of this matrix, okay. How to write it? So this 2 cross 1 matrix of ex at z equal to d and ey z equal to d is equal to matrix of e to the power I phi 0 0 1. So for 2 cross 2 matrix, and then ex of z equal to 0 and ey of z equal to 0. Okay. So this equation I have written it in matrix form. You can check it. You can multiply these two matrix. Okay. And okay, you can ask that why you have written it like this, because it should be e to the power I 5 by 2 here, and here e to the power I 5 by 2, right? Both are suffering from the same phase changes, but since we are interested in relative phase difference, so that's why we have combined the phases. So it's basically you have two waves. Either you move this to 2 pi, or move both of them to 1 to pi and other in this direction to pi. It's the same thing, right? It will lead to a change of 2 pi phase difference. So that's what we have done here. We have taken the phase difference, the relative phase difference, and this matrix is called TPR, which is the basically Jones matrix for phase retarder. Okay. So just remember this. It's okay? Any question? We will solve some problems, then it will be clear if it is not clear now. So shall we move, or do you have any question? Is it fine? Okay. Okay, so next so let's go to the problem. Okay, so the first problem, the x and y components of the electric field is given, the state of polarization is, okay, so this one is very simple. So what it should be? So what is the difference?
Linearly polar.
Sorry?
Linearly polar.
Okay, how? Because the
M pi.
phase difference is m pi, yeah. So it is linearly polarized. Great. Now again one simple, x is given like this, y is given like this. What is the state of polarization? So you can calculate the phase difference, right? Y minus x, it will be minus pi by 2. So minus pi by 2 means B, right? Yeah. Not left circularly polarized, okay? For left circularly polarized, you have to go to 3 pi by 2. Okay, this is fine. Let's go to next one. Okay. Now here at z equal to 0, the field associated with a left circularly polarized beam is given. Okay, x and y component are given, cos omega t, sin omega t. Okay, great. Similarly, the field at z equal to 0 associated with a right circularly polarized is given, this and this. Okay, then the state of the polarization of the superimposed beam at z equal to 0. Okay, so there are two left circularly polarized beam. No, sorry. Oh yeah, okay. So we have to just calculate the superimposed, I mean the oh, we have to calculate the state of polarization of superimposed beam. Okay, I see. X with X and Y with Y. Okay, so you have to, like, for this plus this, and Y is this plus this. Okay, so it's a mathematical calculation. So Ex will be equal to E naught cos omega t plus E naught cos omega t minus phi, right? So you can use the cos formula, cos A plus cos B, right? And what you get, so Ex will be 2 E naught, sorry, cos phi by 2 cos omega t minus phi by 2, right? So C or D could be the correct option. Then similarly you can calculate Ey, and the correct option is D. Fine. It is just, use the trigonometric this identity, cos A plus cos B is equal to 2 cos A plus B by 2 cos A minus B by 2. Fine. Similarly for the sine, you have the other identity. Okay, so now let's go to the problems on Jones matrix. Okay, so x and y components of the electric field is given. What is the normalized Jones vector? So Ex is a cos kz minus omega t, and so this is basically e to the power I kz minus omega t, which we can write as a kate of x, right? And then we have Ey, which is minus b cos kz minus omega t minus phi, which we can write as this, or we can write it as minus b. So let's take the e to the power phi odd, minus phi odd, and you have y, kate y, right? So this is the advantage of writing these in terms of kate x and kate y. Now it is very simple to calculate the resultant vector. So what it be? Ax plus minus b e to the power minus phi y, which is equal to a by, right? And for normalization, what is the formula? This is a square by b square, right? So a square plus minus of b to the power minus I phi square. So this is nothing but just b square. So which is the correct option? A. Right? See how simple is to calculate the resultant vector now. So this is the resultant vector. We have normalized it. Fine. Next problem. Now the state of polarization is described by normalized vector. Okay, so you have been given a normalized vector like this. So now you have to, so this is the reverse of this above problem. Okay, here the normalized vector is given, you have to find the x and y component. So you can, what you can do, you can decompose it in terms of ket x and ket y. So 0.8 ket x minus 0.6 I ket y, right? And then you know ket x is e to the power I kz minus omega t, right? This is what we represent x by, right? So ex is 0.8 e to the 0.8 e naught, sorry, omega t, and ey will be y component will be minus 0.6. So I we can write e to the power I pi by 2, right? E to the power and so this will be e to the power I kz minus omega t plus pi by 2, right? And then when you convert it into cos, this one will be 0.8 e naught cos of kz minus omega t, and this will be e naught. So cos will now become sine or minus sine, shifting pi by 2. So minus, right? So minus minus plus sine kz minus omega t. Is it okay? So this oh wait, no option is matching. Oh no, yeah. What mistake I did? cos theta plus pi by, oh sorry, it is just sine because cos is there, sorry, so minus, yeah, so C is the correct option. Fine. It's very simple, no? You have to just remember this, this Kate notation, like how you represent Jones vector in terms of how you decompose it in terms of x and y. Other things follows from there. So you may ask why you inserted E naught here. It is not given in the problem. Why you inserted E naught? Any do you know why we have to insert E naught? Because this is common factor, yeah, but because this is given here, this is the normalized Jones vector, okay. So that means when you go back from these two to this, right, then what will happen is wait, so when you will go back, so you will have 0.6 E naught y and this. I think E naught should not be here, right? If it is not normalized, then we have to insert E naught. Otherwise, we should not insert E naught here. Logically, I don't know. Because when we go when we reverse this problem, we go back from here to here, then we get a non-normalized Jones